Lesson 102. In this lesson, we're going to look at how we can operate vectors in 2D and 3D. So first of all, just recall that vectors can be represented as ordered pairs on the xy plane. So here, for example, we have vector u with its tail on O, the origin, and an endpoint or terminal point at P at A, comma B. In other words, we can say that this particular vector u has an x component that has a length of a, and then a y component that has a length of b. In vector space, we use a unit vector, a vector that is 1 unit long, along the x-axis. We call that vector I. And a vector that is 1 unit long from origin along the y-axis, this is the unit vector j. Okay? So in this case, because we do have a reference point of 0, or at 0, 0, we call u the position vector of point P. So I, j are the standard basis vectors. So now I can represent vector u, or which is equivalent to vector OP, as follows. I can either call it using the column vector AB, or I can write it in component form, AI plus BJ, okay, as a linear combination of the two scalar multiples of vectors I and j. Okay, and so the vector AB, once again, this is called a column vector. And then AI plus BJ, we refer to this as the component form. Okay. Now, what about vectors in 3D space? It follows a very similar setup. When we discuss vectors in 3D space, we have 3 axes. We have the x-axis, y-axis, and z-axis. So kind of like think about the corner in a box or something like that, okay? So any vector along the x-axis is a scalar multiple of vector I. Any vectors along the y-axis is a scalar multiple of the vector j. Any vectors along the z-axis is a scalar multiple of the vector k, right? Those are the standard basis vectors. So here, how can we represent the vector OP, which has its tail at the origin, ending at point A, comma B, comma C? Well, as a column vector, we can write it as A, B, C, or in component form, we can write this as AI plus BJ plus CK, just like that, okay? So let's take a look at example 1. Given we have vectors PQ and RQ in component form, we want to write vector PR in component form and then as a column vector. So let's draw out these vectors. The one that we want is vector PR. So that goes like this. And I know that this is a resultant of the vector. I will have to start from P, right? So vector PQ plus the vector head to tail connection QR. So let's write out this vector equation. PR is equal to PQ plus QR. So I was given PQ as 2I plus 5J minus 2K. But instead of, having QR given to us, I got RQ, which is the opposite of QR. So we can say that we're going to add the opposite of RQ, which is positive 2J minus 4K instead. Okay, maybe on the side, I'm going to write down. Like that, okay? So to operate vectors, it's very simple. These components are independent of each other. So in a way, it feels like you're working with algebra, you're collecting like terms. Now here you're collecting the like components, you're adding the components. So I have 2i, no other i's, so that stays. I have plus 5j plus 2j, so that's plus 7j. Minus 2k plus minus 4k, that would be minus 6k. So this is PR vector in component form. If I have to express this in column, as of column vectors, 2, 7, and negative 6. So on this page, we have outlined the different properties of vector addition and scalar multiplication when we express vectors in either component form or column vectors, and it's missing here, okay? So you can find the similarities that we're always grouping like components, like the same components together. Same component form, you're technically adding all the i's together and then all the j's together, okay? As column vectors, you add across basically the I components or the X components, and then you add the Y components, just like that. So it's pretty straightforward, okay? In terms of properties of scalar multiplication, we can apply the associative law and distributive law when we deal with vectors. So m times n, two scalar values multiplied together times vector A is the same as multiplying m by the scalar multiple na, or you just get the same result as m times n times a, resulting in still a vector quantity. Using the distributive law, it's kind of like the distributive properties that you learn when you work with polynomials, right? You would distribute your scalar multiple into the brackets where you're adding two vectors together, or when you are adding two scalars and then multiply by a vector, you can do individual scalar multiple of the vector before you add them together. They're just equivalent, okay? All right, so let's use the property of real numbers to show the following properties. So let A be the vector mi plus nj, and B be the vector xi plus yj, where m and xy are all real numbers. So how do I show a plus b, vector a plus a vector b is the same as vector b plus vector a? We can start from a plus b, and then a is the vector mi plus nj plus the vector b xi plus yj. Okay, I know that I need to group like components together when I'm adding, and then after that I can use commutative law to switch the order of addition and subtraction. So I can say that, well, because adding order doesn't matter, I can say that I have xi plus yj and then plus mi plus nj. So I'm switching the order of addition, and now if I consider grouping the terms together, now I see that I have vector b plus vector a. Okay, so here we are using the commutative law of addition. Okay, now what about scalar multiples here? So I can start by showing PR times A, and this gives me PR as a scalar multiplied by the vector mi plus nj. And then I have P times R times mi using distributive property plus PRN times j. Now I can do some association because I want to show this is the same as P times R times A, right? So I'm going to factor P, and then inside this I can factor R again. Okay, and so here I have P times R A. Going back to this line where I have the expanded form, what if I want to show that this is also equivalent to R times P times A? Basically, you do something very similar. So we have PR times A equals to star. And now instead of factoring out P first, I'm going to factor out R first, then factor P. And this is R times P A. Example 3. So we're given three vectors x, y, z. We want to express x minus 2y plus 3z in terms of I, j, k. All right, so let me write down x minus 2y plus 3z. And substitute the corresponding, component form of these vectors. So x is I plus j minus k, minus 2 times y is 2i minus k, plus 3 times 2j plus k. So let's work out the scalar multiples first. Here I have negative 4i plus 2k. And then I have 6j plus 3k. Okay. Now we have to add the different components, right? So I have I minus 4i, that's negative 3i. J plus 6j is plus 7j. Minus k plus 2k is k, plus 3k, 4k. And that's it. So very similar to working with polynomials. Example 4. Determine M such that the pair of vectors A and B are collinear. All right. So recall from the past that there is a vector operation that can relate to the keyword collinear. And it is scalar multiple, right? So let's write this down. If vector A and vector B are collinear, then KA must equal to B. Or if you like, you can say A is equal to KB. It doesn't really matter. So here, let's put in A, which is the column vector negative 2 and 3. This is equal to M, 24. We can compare components. We got negative 2k equals to M. We also have 3k equals to 24. So these are the two equations. From the second equation, I can work out k is equal to 8. And so if I plug this into M, I have 2 times 8 equals to M. And so M must be negative 16. Okay? And so let's make a conclusion. Therefore, k is equal to 8 and M is equal to negative 16. Okay, example 5 now. Given two vectors A and B, find the value of the scalar P such that A plus PB is parallel to the vector 1, 7, and 3. So similar to number 4, we have keyword parallel, and this time it's a linear combination A plus PB parallel to the vector 1, 7, 3. So it's not enough just to express our equation like this, but we have to show that we're looking for a scalar multiple of 1, 7, 3. Okay? Now substituting A and B into the left side of the equation, I can show that we have 3 plus P times 1 in the X component, 7 plus 0 in the Y component, and 1 minus P in the Z component. Okay? And this is equivalent to K, 7K, 3K. when I compare the components, I have 3 plus p equals to k. I have 7 equals to 7k. I have 1 minus p equal to 3k. Okay, this is a system of equation. And from the second equation, it's clear that k is equal to 1. Okay, so now let's move to the side here. If k is equal to 1, okay, what happens to the two equations here? I have 3 plus p equal to 1. P is equal to negative 2. And if I sub it into equation 3, 1 minus p is equal to 3. P is equal to negative 2 as well. It is actually essential to check this step to make sure that, the k value of k equals 1 will give us a consistent value in p amongst the two other components in the vector equation. Okay, so since the value of p is unique, therefore p must equal to negative 2. Okay, we have to have that consistency. Moving on, we are going to now look closer at position vectors. So like we mentioned before, a position vector is the displacement of a point from the origin. So here I have a x1, y1. So I can say that the vector OA, okay, is the position vector x1, y1, and the vector OB, okay, is the position vector of x2, y2. So what are we asked to do here? Okay, we want to write a displacement vector AB in terms of position vectors OA and OB. So looking at the diagram that I have here, I know that the starting point of vector AB is actually the point A. So I can say that, well, AB is equal to AO plus OB. The vector AO is negative of OA. Let's clean this up. We can say that AB as a displacement vector can be represented by OB minus OA. There is significance in this relationship because here AB, we call this the displacement vector. OB indicates the final position, okay, of the displacement, and OA is actually the initial position of the displacement vector. Okay, so if you study physics, you know that displacement is a change in position, like delta D, right? So D2 minus D1. So same idea here in math. So let's take a look at example 6. The points A and B form opposite diagonal corners of a rectangular prism. So let's sketch this prism, okay? All right, so let's see. I have to find point A. Oh, let me label my axes. This is X, Y, and Z. It forms that orthogonal. And point A is I go one step along. Let me try to do this. So I go one step from the origin along the x-axis, 0 steps along the y-axis, so no change in that, I stay here, and then 5 up the z-axis, so 1, 2, 3, 4, 5, like that. So, yeah. Okay, so let me delete this. I'm just going to draw it by hand. 1, 2, 3, 4, 5. Like here. Here's point A. Okay, so this is A. And then B is 0 to 0. So I start from the origin, only go 2 steps, okay, on the y-axis. And then I need the prism now. Let's see. So it should be 1 unit this way, 1 unit, 2 units that way, and 1 like that. 5 up. 1, 2, 3, 4, 5. And then let's finish the prism. Like that. So this is the trickier part. And then something like this. And then complete the vertical. Okay? And now we're asked to find the vector A, B in component form. All right. From the introduction to position vectors and displacement, I know the vector AB is OB minus OA. So OB is 0, 2, 0. OA is 1, 0, 5. Okay. So here I have negative 1, 2, and negative 5. Part C. M is the midpoint of AB. Find the position vector of M. So I think I'm going to sketch in the line segment AB, and then roughly here would be the midpoint M. And we're looking for the vector OM, the position vector. Okay. So looking at this diagram here, I think I see a vector equation that can be formed. OM can be represented using the vector OA plus the vector AM to close off that triangle. Okay. So I know what OA is, but I don't know M, so I can't find AM directly. But AM is a vector that sits right on the vector AB. But M is halfway, so I can say that we are adding OA to half of vector AB, like that. So vector OA is 105 plus vector AB we found in part B, multiply that by a half. I have negative 1 half 1 negative 5 over 2. Okay, which works out to 1 over 2, 1, and 5 over 2. Okay, so this is the vector OM. You may also notice that this is a vector that is half of the sum of vector OA plus vector OB. So let me write this down. Okay, so once you know this relation, you can apply this directly to find OM next time. Okay? And this is the end of lesson 102.